So we are the anonymous authors of this assignment 4. We are taking the course Computational Tools for Big Data, and our assignment 4 title is Using Docker to Deploy an Apache Spark Cluster. So what is Docker? Basically, Docker is an open source project which tries to fix the problem of shipping code to a server. It makes it easier to create, deploy and run applications by using containers. It's basically both like an help to developers as well as help to system administrators. Docker uses containers, which works sort of like a virtual machine, except that it doesn't create a full virtual machine operating system. Instead, it relies on the underlying Linux kernel of the host, and this basically means that it can achieve a low overhead and lower size than traditional virtual machines. It basically only needs the applications and libraries necessary to host the software contained in the container. So to build a Docker container, we must first specify a Docker file which holds the information about a Docker image. A Docker image is a basis for containers. So each time you create a container, it's basically created from a Docker image, which is sort of like a blueprint. Basically, like I said before, the applications are many. It's used to sort of create a homogeneous environment. So the thing we're going to use it for is to deploy Apache Spark nodes, and using an application like Docker, we can ensure that the same version of Spark and the same scripts and the same whole setup is present in all of the nodes available in the cluster, as well as both the workers and the master itself. So what we're gonna create is some worker containers and a Spark master container and a container for running the actual scripts on the Apache Spark cluster. So it's time for some Docker basics. So to use Docker, you just type Docker into the shell. You can do it both as root or just as a normal user, but as a normal user you have to add your user to a special group and stuff. So we just do it with sudo for now. So basically these are the commands you can do on Docker. So you can do Docker images to list the number of images available to us. So we can actually run, let's say I want to run the Ubuntu image. We do a sudo docker run Ubuntu 14.04, and we just want to run the bash shell. And we do it with the flags int, which creates a sudo t2y and allow us to make input to the container. So right now I'm basically in the container with its own file system. It's got a file system, it's got networking capabilities. It's basically just like a small version of Ubuntu. It's got applications. We can do a package index update that actually allows us to install some files. So we can just install we can install normal files and applications like in regular Ubuntu. So you can just run cowsay. It's user games. There. So we basically have access to all the normal Ubuntu applications. So right now, when we're in this container, we can basically open a new container, a new tab. Do a Docker PS. Which actually allows us to see which containers are are active right now. We can even do a Docker diff with just the name and see which files are different from the base image. So yeah, we can see a lot of app files, also some Causa files being installed. And we can actually also do a Docker commit if we wanted that. So a lot of ways it's the same as Git, where you can do a diff and you can do a commit to commit a new image from the container where you've installed a lot of things. So now I'm gonna explain our Docker file, which is the file Docker uses to convert into an image basically, and which we then use to create our containers from. So let's just do this. So basically our Docker file is from Ubuntu 14.04, so this is the base image. The maintainer is Pagomov Igor. This is the guy we got the Docker file from and modified it from. So these lines right here, the run instructions, are basically what's run inside the image before it is created, and these lines are just the preliminary updates of getting the apt-add repository command and then installing Java on the image. This next line here is installing curl and then getting a Spark binaries, and then extracting them in user local and creating a symbol link. So these right here are our scripts, which are added, which are contained in the scripts folder, and are then copied to the image. These env are environmental variables we need, so Spark home for Apache Spark and the Python path as well. And these are the ports and just generally the settings used for the Spark master and Spark worker. And these are the ports. So we set them as environmental variables, and then we expose all of these ports because the Apache Spark master and Spark workers need them exposed. So basically from that Docker file we created a small shell script which uses Docker to build the image from the Docker file, and can run it like this. We're using cache for all of it because we already have the image. So as we saw in the script, we called it test, and we can see that we have it right here under images as well. So basically the scripts we saw before, which are copied to the container, are contained in the scripts folder. So basically the important ones are the Spark submit script, which exports the local IP of the container and then runs Spark submit with the Spark master IP and port and the Spark default config file. So the Spark default config file is this one, just specifying which ports and the broadcast factory of Apache Spark. And yeah, basically all of these are like sort of the same. So the master is just run with the Spark default configuration file as well, and the local IP, and it also exports the Spark master IP, and the worker is run with the Spark default configuration file as well as setting the Spark local IP, the host main to listen to, and the Spark master IP and Spark master port. Those are basically the scripts we use. And basically for running a script on it, we use the exercise from the Apache Spark week. So we use this word count exercise, and as you can see here, we have defined that it should use the Spark master IP and Spark master port. So what we can do now is run these run a master, and these scripts in the root folder are basically just encapsulated scripts that basically just starts a container and then runs the corresponding or respective script in the container. So this runs a new Docker container, runs it detached, and it runs it creating a sudo TTY exposing the ports to the host as well, and it gives it the name Spark Master. So we can just run the master. We need to start Docker first. There we go. So we can start the master like this. So basically the master is started now, and you can check that it is by using this command. So basically this is the master container that just started, and we can see the ports being mapped. So all is good there, and then we can start a worker. There we go. And so I should probably explain the Spark submit script we created as well. So basically what this script does is it just starts a Docker container with keywords IT, which creates a sudo TTY, and it creates it detached with the D flag, links it to the Spark master, and exposes the ports to the host. So we just get that container ID, and we copy the first argument, which is the exercise Python file, and the second couple of arguments with this, which is eventual or like data files used by the script. So we execute Spark submit with that argument, and then we stop and remove the container. We can actually just say Spark submit exercise 9.1 exercise 1 data. So there we go. So right now it's trying to run the exercise, and it succeeds. So this is the word count for a large lorem ipsum file of 17 megabytes in 3.2 seconds. And we can see it used a worker with the IP 172.17.03. So right now we can basically start multiple workers if you wanted to, and just run the same script again. Yeah, there we go. And from the output we can actually see that it runs on both 172.17.03 and 04 as well. So it's actually running on two different workers now. So our last notes are that we have succeeded in deploying Apache Spark in Dockerized containers on a single computer. So the next logical step and further work could be spent on deploying it to multiple computers, multiple physical nodes in a local area network.